Hello and welcome to our presentation on oscillation and waves. We are group number 1 and today we will be exploring the fundamental physics concepts that describes everything from a swinging pendulum to the light from your screen. Let's get started. Our goals for this presentation are threefold, following the KSA model. By the end, you will be able to explain the differences between types of waves and motion, solve for wave characteristics like amplitude and frequency, and relate the importance of these concepts to daily life. We will cover key topics including damp motion, wave types, and the sinusoidal wave function. Now, I'll pass it over to Alfie to dive into the core concepts.
Thank you, Jill. Now, let's begin with the basics. An oscillation is simply a repetitive back and forth motion, a wiggle in time. A perfect example is this pendulum swinging. We describe this motion with two k quantities. First, the period, or capital T. This is the time it takes to complete one full cycle, measured in seconds. Second, the frequency, or lowercase f. This is the number of cycles that occur every single second, and we measure it in hertz. And in these two concepts are intimately linked. They have an inverse relationship, as you can see from the formula. Frequency equals 1 divided by period. A high frequency means a very short period, and vice versa. For example, a string that vibrates 440 times per second has a frequency of 440 Hz and a period of just 1 per 440th of a second. Now, a very important and specific type of oscillation is called simple harmonic motion, or SHM. This occurs when the force restoring an object to its center is proportional to its displacement. A mass bouncing on a perfect spring is the classic example. You'll notice two things here. First, the, the maximum displacement is called amplitude. Second, the period of this spring mass system is given by this formula. T equals 2 pi times the square root of mass over the spring constant. Crucially, the period depends only on the mass and spring's stiffness, not on the amplitude. Small bounce and a big bounce take the same amount of time per cycle. Now, Elea will discuss what happens when we introduce real-world factors.
Thanks, Alfie. In ideal, frictionless world, that mass on the spring would bounce forever. But in reality, oscillation loses energy to friction and air resistance. This is called damping, and it causes the amplitude to decrease over time. There are three types that we needed to know. First is underdamp. This is what we most commonly see. The system still oscillates, but each swing is smaller than the last, like a swing gradually becoming to stop. Second is critical damp. This is energy sweet spot. The system returns to equilibrium as fast as possible without oscillating past it. This is exactly what we want in a car shock absorber. It stops bouncing immediately to stop the tires on the road. Finally, overdump. Here, the system is so sluggish that it returns to equilibrium very slowly without any oscillation at all. Imagine a door closer filled with thick honey. It will just slowly creep shut.
Thank you, Elijah. So, while an oscillation is a wiggle in time, a wave is a wiggle in both space and time. It's a disturbance that transfers energy from one place to another without transferring matter. Waves that need a medium to travel through, like water or air, are called mechanical waves. Let's look at the structure of a wave. The highest point is called the crest, and the lowest point is the trough. The distance between two identical points, say from one crest to the next, is the wavelength, symbolized by the Greek letter lambda. Now, there are two primary types of mechanical waves. The first is a transverse wave. Here, the particles of the medium move perpendicular or at a right angle to the direction the wave is traveling. Think of a wave on a string. You flick your hand up and down, but the wave travels horizontally. Light is also a transverse wave. The second type is a longitudinal wave. Here, the particles move parallel to the wave's direction. This creates areas of compression where particles are squeezed together and rarefaction where they are spread out. The most common example is sound. When I speak, I create compressions and rarefactions that travel through the air to your ears. Now King will introduce the mathematics that describes all of this.
Thanks, Jake. To accurately model and predict wave behavior, we use a powerful tool called the sinusoidal wave function. This equation, y of x and t equals a times sine of kx minus omega t, allows us to calculate the wave's position at any point in space and any moment in time. Now, let's break down the key variables. A is the amplitude, the wave's maximum height. Then k is the wave number, which is defined as 2 pi divided by the wavelength. It tells us how many waves fit into a unit of a distance. And omega is the angular frequency defined as 2 pi times the frequency, or 2 pi f. It tells us how rapidly the wave oscillates in the radians per second. Finally, the wave speed can be found in two ways or can be solved in two ways. The classic speed is equal to frequency times wavelength, or equivalently, speed equals angular frequency divided by wave number. Alright, so let's have an example problem here. For the example problem number 1, we have a wave is modeled by y of x and t is equal to 0.2 m sine of 6.28x minus 1.57 t. Now, we're tasked to find its amplitude, frequency, wavelength, and speed. First, find the amplitude. It's already given in the equation, which is 0.2. So that's our amplitude. Next is for the frequency. So to find the frequency, we all know that angular frequency, or represented by the lowercase omega, is equal to 2 pi f. To find f, all we have to do is rearrange the equation. So to find f, all you have to do is divide both sides by 2 pi. Then cancel. So we're left with f is equal to 2 pi. F is equal to omega over 2 pi. Now, let's solve for frequency. The frequency is equal to our omega, or our angular frequency, which has the value of 1.57 divided by 2 pi. So if you plug in that in your calculator, you'll get a value of about 0.25 hertz. So that's the value of our frequency. Let me write it real quick. Frequency is equal to 0.25 hertz. Now, let's find the wavelength. And we all know that the wave number is computed or solved by using the equation k is equal to lambda times 2 pi divided by lambda. So to solve for the wavelength, wavelength also is represented by lambda, this Greek letter. So to solve for the wavelength, all you have to do is first rearrange this equation by multiplying both sides by lambda, so that cancels out. We're left with 2 pi, or 2 lambda k is equal to 2 pi. And to get lambda, all we have to do next is divide both sides by k. That cancels out. Now we're left with lambda is equal to 2 pi over k. And plug in the values. Our k is, according to our equation, is 6.28. So 2 pi divided by 6.28. And if you plug that in your calculator, you'll get a value of 1, about 1 meter. So that's the value of our wavelength. Wavelength is equal to 1 meter. Next, finally, for the speed, to solve for the speed, we'll be using the equation V is equal to lambda times frequency. And let's plug in our values. Our lambda is 1 meter times the frequency 0.25 hertz. So that means the value of our speed, wavelength speed, is 0.25 meter per second. And that's it. So let me state that one quick. And V is equal to 0.25 meter per second. So this is the answer for the example problem number 1.
Thank you, King. So, why does all of this matter? The physics of oscillations and waves is not just about abstract theory. It is the foundation of so much modern technology. Think about clocks, which use the precise oscillation of a pendulum or quartz crystal to keep time. Think about music, where the frequency of a vibrating strings or air columns determines the pitch we hear. In medicine, ultrasound uses high-frequency sound waves to create images of our internal organs. And in communication, all of our radio, Wi-Fi, and cellular networks rely on transmission and reception of electromagnetic waves. In summary, we have seen that oscillations are repetitive motions in time, governed by period, frequency, and simple harmonic motions. And waves are how energy travels through space, characterized by their wavelength, amplitude, and speed, and can be transverse or longitudinal.
And that concludes our video. Thank you for listening. Have a good day.